Welcome back. Today, we are diving into the core concepts of calculus of variations. We will learn how to map entire functions to numbers and how to measure their size using norms. Let's start with the basic idea of a functional. Imagine we have a set of functions, which we call a function space, and we denote it by capital M. A functional is a rule, usually written as capital J, that assigns a real number to each function y of x in that space. So we write J maps M to the real numbers, or J maps M into R. The functions that belong to the domain M are often called admissible functions. Now, here is the key distinction. A standard function maps a number to a number. X goes to f of x. But a functional maps a whole function to a number. Y of x goes to j of y, or j bracket y. For example, if f of x equals x squared, and we input x equals 2, the output is 4. But if we define a functional j of y as the integral from 0 to 1 of y of x dx, and we choose the function y of x equals 2x, then the output is 1. A classic example of a functional is the definite integral. It takes an input function y of x and produces a single scalar value. We define it as j of y equals the integral from a to b of y of x dx. Geometrically, this output represents the area under the curve between x equals a and x equals b. So the input is a function, the entire curve, and the output is just one number. Next, we need to be precise about what kinds of functions we allow as admissible. In calculus of variations, we often work with function spaces where functions are continuous, and sometimes their derivatives are also continuous. We use the notation c superscript p on the interval a to b. This means the function has continuous derivatives up to order p on the interval a to b. So, c0 on ab means the function is continuous. c1 on ab means the function is continuous and has a continuous first derivative. And higher p means more smoothness. On the picture, you can think of c0 as allowing corners or sharp changes, while c1 is smoother, and cp is even smoother, with continuous higher-order derivatives. Now, we define a norm on these spaces, a way to measure the size of a function. Here, the norm is defined as the cp norm of y equals the sum from k equals 0 to p of the maximum over x in ab of the absolute value of the kth derivative of y. In other words, we take the maximum absolute value of the function itself, then the maximum of the first derivative, and so on up to the pth derivative, and we add them together. Let's compute an example for y of x equals sine of x on the interval 0 to pi, and we take p equals 2. First, the maximum of the absolute value of y of x, which is the absolute value of sine of x, is 1. Second, y prime of x equals cosine of x, and the maximum of the absolute value of cosine of x is also 1. Third, y double prime of x equals negative sine of x, and the maximum of the absolute value of negative sine of x is again 1. So the total is 1 plus 1 plus 1 equals 3. That means the c2 norm of sine of x on the interval 0 to pi equals 3.